Greetings, everyone. I'm Dr. Nishat Fatima Mohammed. It's my most pleasure to welcome you to my presentation on lung cancer prediction through machine learning algorithms as my final project for DA5030 at Northeastern University, Boston. So lung cancer is the most common cancer worldwide and in women, and it is the most common in men. It remains deadly because we are unable to detect cases early with several negative environmental factors on the rise. The disease progression and the metastasis is far faster than we expect. And early detection is paramount for the patient and to screen their closest relatives, as well as having a multifold effect on the patients, their relatives, the researchers, and the medical teams. I aim to predict tumor cases of squamous cell lung cancer using RNA-Seq data obtained from TCGA, which is a renowned cancer database that is open source and has benefited many. The dataset was obtained from Kaggle and in form of a zipped CSV file of about 230 megabytes. And the data analysis was carried out on Discovery platform of the Northeastern University. And yeah, so just sit back with a delicious cup of your favorite beverage and relax while I take you through my work. So I'll just put you through. This is the Discovery platform. I'm logged in and I'm going to take a run and start a job on the RStudio Rocker container. Here you can see my job is already started. I'll click on the Connect RStudio server and it will take me to my RStudio and my script over here. And let's go back to my presentation. We've loaded the packages required. I've loaded the data over here from the CSV file, looked at the structure and the head, although I've not printed that because it's humongous with these dimensions. You can notice that the genes are in the rows and the patient IDs, instances of those genes are in the columns. So this transposition of the dataset was paramount at this stage. Now you can see we have swapped the columns with the rows and the rows with the columns. Here I have named some of the columns. I took off this later on. I checked for missing values and I didn't find any. I looked out for zeros and found so many of the instances had zeros for a couple of the genes, so we'll be finding zeros in all the rows and all the columns. So the best way I thought to handle this was to remove all the variables that had zeros for every instance. This reduced the dimensions to 55 plus from 56,000 columns. Now I have looked at the distribution of the classes in the outcome variable and we can see the imbalance. I encoded the outcome variable here and transformed all the variables to numeric from character class, visualized generally using a PCA. The red is for the tumor class, obviously, and the black PC principal component is for the normal. It's kind of like in the background, but you can figure that it's about this dimension. I also looked at the components on a scree plot just to see the variance among them. Then I balanced my data. First, I did a demo on a subset, and then I balanced it using the imbalance package. I leveraged random oversampling. I also tried out rows and smooth, but these didn't work out for me. And thus, I used the RWO function from the imbalance package in R. After balancing, you can see the distribution is this way. This is the normal now, and this is the tumor class. And our rows have increased to 1,051. Now I went ahead again to do a principal component analysis to achieve dimensionality reduction. After a scurry plot, we can see a slight change from the previous. And here I did the dimensionality reduction. I picked the top 30 principal components, and we'll be working through with them. I checked out the correlation between the principal components using the Pierce panels function from the psych package, and you could see 15 per panel per visualization here. And I checked the correlation with the Spearman method, and I'd like to mention that this data is distributed by negative binomial, and also it has already been normalized with the TPM. Here I do the data splitting and stratification. So I picked a equal percentage to represent each class in each training, validation, and test set. And the training set is 70%, and validation 15%, and test set 15%. And the dimensions have been visualized here. For the scaling of the data, I did the scaling separately for each set. And here I have spoken about the use of TPM, that's transcript per million, instead of RPKM and FPKM. This is a far better method, and we already had this done before for the whole data set from the start. Now, the scaling parameters method is the min-max scaling using the scale function. Here I have done it for the validation, and here you can see all the values for each set are now from 0 to 1. Finally, we go to random our modeling. So I used random forest because it is it's really great. It's an ensemble model. It can show us the importance of a barrage of features. It handles dimensionality nicely. It provides us with ways to handle failure of the models, be it overfitting or underfitting. So here I have trained the model after doing factoring of the outcome. Here I trained the model and using hyperparametric tuning on the number of trees, 10, 15, 20, to 50, and the best outcome was with the 20 trees, I think 20 trees or 10 trees, I think, yeah. Yeah, the third model was the best with 20 trees. And then I looked at the entropy using this plot just to see how the variance is distributed and how much entropy is contributed by the principal components that I'm examining. And then here we go to evaluate on the validation set with confusion matrix to evaluate on the accuracies of each module. And finally, I come down to the model, which is the third model I feel is the best among them with an accuracy of 75. I evaluated again using the K-fold cross-validation. Here I have repeated 3 times on 5 subsets of the training set, and I've validated with the validation set, and the accuracy is slightly it's almost the same as for the previous model. In fact, it came down a little from 75 to 70% accuracy. And here you go with the ROC. I have a better view of the third model and the 6th model over here. So yeah, it's cool. And let's see. Yeah, the 6th model looks like a great one. Yeah, compared with the third, but I'll still be afraid of some form of overfitting. And again, I use the 6th model to look out for the entropy. And here I'm looking at the feature importance. So PC2 and 1 are looking like the most important among the rest. C5 model package was used for decision trees to compare on complexities of random forest and decision trees separately. Here we found a nice accuracy of 70%, and did the ROC comparing the third and the first baseline base model for the C5 decision tree, and I boosted it using the grid, and I did a cross-fold validation. Here's the grid for the boosting, and here's the those validation parameters we used. And then we went ahead here to check out the accuracy. Didn't really improve for both models. Here you can see on the ROC curve, both models lie on the same line. They look a little bit better than random forest for the obvious reasons that they're more prone to overfitting than the random forest. So they will be considered as not so good as the random. Now the support vector machine model here was chosen because it handles high dimensionality. It gives us great options to handle overfitting through regularization parameter. Here is the cost. We also have options to choose on the kernels. Here I choose the linear to train our baseline model, and we got a whopping accuracy of 90%. And after validation, accuracy slightly increased to 96.82 of an overfit model. We improved the model with the regularization. Cost of 0.1 gave us a training accuracy of 0.1 here, and giving a range for the cost also kind of like gave us a training error of 0 for the best on that, with a cost of 1. And so I chose the baseline model over here, and yeah, so the baseline model was taken as the best one. I tested out the radial kernel, but it didn't really work out. You can see the ROC curve is really linear and doesn't make any sense. So I scrapped the radial kernel and chose the linear one. ANN models are great because they can pick patterns within your data, and it will also provide us with a lot of options for tuning and stateful cross-validation evaluation as well. So here I took the neural net tools to make my NN-based model over here. You can see a whopping accuracy of 95% with a kappa of 29. And this is our input layer. The hidden layer has one node, and the outcome is over there. After this, I evaluated on the validation data with accuracy dropping to 54. That's a huge change. So I'm thinking this model is fitted as there's a large change in parameters, and plus I try to fine tune the model by using the hyperparameter tuning on the decay and the size. And here you can see I finally have a 7 node hidden layer incorporated into the model, and evaluating it on the validation data gave us a 99% accuracy. Okay, so comparing all the models, here you can see all the parameters, and SVM looks great with ANN performing the best. SVM took a shorter time than the ANN. The fastest was the C5 because of its low complexity. And I finally made the heterogeneous ensemble model using all the 4 models, and I took a majority vote on them, and I compared them in the ROC, compared with them on the accuracy parameters, and the ensemble model was closest to the SVM model based on the accuracy parameters. And finally, I have held on to the testing data, and now I would like to test my ensemble on it. And finally, with the testing data, our accuracies kind of dropped slightly by 1%, which is quite minimal. pointing to minimal overfitting. So I would trust my ensemble model best. And in conclusion, I have leveraged four machine learning models after cleaning up my data, and I have hypertuned each model and cross-fold validated each model, attaining a heterogeneous model, which gave me an 89.2% accuracy with a harmonic mean of 87%. So thank you for listening, and I'd like to thank my instructors, Dr. Amina Sari, and the teaching assistants who have helped me through this course. Thank you for teaching me. Thank you for being patient with me. Have a great day.